This is the Jacobian. We're going to be doing a 3x3 matrix, and this is video 2. Make sure you watch video 1 for an introduction, as well as working on a 2x2 matrix before you start a 3x3 matrix. In the book, we have a problem number 3, page 187. The problem is given here. The book gives x1 is y1. Note that all x's must be a function of y only. So x1 is good, x is a function of y. When you go to x2, you can see that we have y2, that's fine. However, divided by x1, we can't leave x1 here. We must rewrite x1 as a function of y. We know x1 is y1, we replace y1, and we get then y2 over y1. This process of writing every x as a function of y only must be done in any problem before you try to find the Jacobian. Let's look at x3. x3, we have x3 and y3 on top. At the bottom we have x1 and x2. Well, we must replace x1 and x2 as functions of y only. When we replace, we know that we get x1 equals y1. So I put y1 for x1. And x2 we just found here. x2 is y2 over y1, y2 over y1. Simplify, and we end up with x3 is y3, y2. And as you can see, we have x1, x2, and x3, all three as functions of y. We can now proceed to find the Jacobian. The first thing we're going to do is to set up a Jacobian matrix. I put all the three functions here again, all the three x's as functions of y. Note that when you set up this matrix, you must keep the x's by row. So x1 is row 1, x2 is row 2. You can see here x1 row 1, x2 is row 2, x3 is row 3. Now, the y's are columns, so you can see that column 1 has y1, column 2 has y2, column 3 has y3. It's now time to start doing these partial derivatives. Here's the process I mentioned in video number 2. Put your finger here and keep it here until you're done with the entire row. So row 1, we are doing this function over y1. Well, the derivative of y1 is number 1. Got it there. Keep your finger there. Move to the second. Now it's this function over y2. There is no y2. Therefore, the derivative is 0. Keep your finger there. Move over to the third cell. It's this function over y3. Look there. No y3. The derivative is 0. Row 1 is done. Move your finger now to x2. You start row 2. It's this function over y1. y1 is in the denominator, and therefore you need the quotient rule. The variable you want is in the denominator. That's quotient rule. So quotient rule for this case, y2 over y1, is going to appear right here. Here is the quotient rule for that very case. We're going to keep the y2 here. Once we put it up there, we take the derivative of y2. Note that we are doing the derivative of that function over y1. So y2 is a number, therefore the derivative is 0. The minus sign for the quotient rule. Now we keep the y2, and the derivative of y1 over y1 is number 1. Then we square the denominator, cancel this part, the minus sign transfer, and we get the partial here. So back to our matrix. The partial is right here. Now our finger was here. So we're going to work on this cell now. We're going to do this function over y2. Note now that for this cell over y2, you can see that y1 is a number. Therefore, it stays y1. We only take the derivative of y2. The only time you take derivatives in the quotient rule is when your variable is in the denominator. For this cell, which is over y2, the variable is not in the denominator, therefore the denominator is a number. The derivative of y2 over y2 is number 1. The y1 stays, and you're going to see it right here, 1 over y1. We proceed in this manner to complete all the derivatives, and now we have a matrix of partial derivatives. I'm going to leave the camera on the other cells so you can see here how you're going to take the derivative of x2 over y2 right there, and x3 over y2. It's right here. The quotient rule is right here, and here's what goes in the matrix of partial derivative. So now our matrix ready. We're going to see how we find the Jacobian for a 3 by 3 matrix. It's a 3 by 3, so there is something new here. What's new when you do the Jacobian for a 3 by 3 matrix? You pick a pivot point, and we're picking the corner point. Note that you can pick any row to be your pivot row. However, here's the hint. Before you decide, look at your matrix. Your Jacobian matrix has zeros, has 2 zeros in this row. You want the row with the most zeros, so you work less, okay? You could pick the second row, but it only has 1 zero, so you're going to work a little more. But the first row has 2 zeros, so you want the row with the most zero. So we chose the first row to be the pivot. So what happened is that this is the pivot from linear algebra. You lock in the pivot, then you cross the row and you cross the column where the pivot is. Once you do that, you end up with these 4 cells with no crossing. These are the cells that are going to come here. And this is a 2 by 2 matrix that is going to be multiplied by that pivot. So this pivot multiplying this matrix. Now, once you set this up, put a minus sign. You only put a minus sign once, because the minus, there is a reason for it in linear algebra, but you have to put a minus before you do the second pivot. Now, when you go to the second pivot, we're moved over here. So you can see that I picked this to be the pivot. The arrow is pointing to it. Cross the row where the pivot is, cross the column where the pivot is. Now we have these 2 pieces that are going to come over here. And this pivot times the 2 by 2 matrix determinant. Plus, you put a plus before you do the third pivot. Here is the third pivot. I marked it with an arrow. Cross the row, cross the column. We have these cells that are going to come into this 2 by 2 matrix. This pivot multiplies this cell, which means that pivot 2 by 2 minus pivot 2 by 2 plus pivot 2 by 2. This is going to give the determinant. Now, looking at our matrix, we would do these 3 pivots, but when I go to the minus pivot times the 2 by 2, this is 0 times. It's going to give a 0, it's going to give a 0. So for this matrix, really, the only thing I need to do is the first pivot times this 2 by 2, and then I find the determinant for this 2 by 2. So let's see how that goes. Because here I have a 1, I take this pivot times this 2 by 2. Note that this would be crossed out, and I get this. So here's the matrix. Now, the determinant of a 2 by 2, like I showed in the previous videos, it's this diagonal multiplied minus a minus sign, this diagonal multiplied. However, when I multiply this diagonal, I have a 0. So this is going to be 0. I don't need to multiply it. Therefore, the determinant is just 1 times this diagonal, which gives 1 over y1, y2. So now, this is the Jacobian, and like I said before, we always use the Jacobian as absolute, and once I'm giving numbers for y1 and y2, this becomes a whole number, and that's why it comes out of the triple integral, because it's a constant now. And then I integrate function of x, y, z, dx, dy, dz, multiplied by this. So this Jacobian here is indicating how much change occurred in the image after I did a transformation from x, y to u, v. In this case, it's a transformation. It's a 3 by 3, so it's x, y, z for into u, v, w.